Hi, everybody. I'm going to talk about the main mechanisms of strong nucleophiles with carbonyls in this video. There's going to be a few mechanisms that we're not going to cover here, but I kind of wanted to give a really focused short look at the ones that crop up the most. So the strong nucleophiles that we're looking at, they are these guys. So lithium aluminum hydride, organolithium reagents, Grignard reagents, and sodium borohydride. So these are kind of the strong nucleophiles that we're interested in right now. We have a couple of them are hydrogen nucleophiles. Okay, so they're kind of an H- equivalent. And then some of them are carbon nucleophiles, where remember we want to think about this as if our H's are on the aluminum, our aluminum is less electronegative than the hydrogen is. So the hydrogen is actually holding those electrons. Okay, same with the boron over here and the hydrogen. Hydrogen's actually holding those electrons. For these two, same kind of situation. We've got lithium and magnesium, both of which are more electropositive than carbon atoms are. So that's going to make all of these hydrogens and carbons be actual nucleophiles. And so we're going to have a lot of new options in terms of CH and CC bond formation, which is pretty cool. So I want to first talk about the mechanism with aldehydes and ketones. So when we've got an aldehyde or a ketone, we're going to have one of those two functional groups present. So we can have something like this, where I have my R groups, got my carbonyl, and R1 and R2. They can be carbon or hydrogen, or both of them, or neither, right? Well, has to be those carbon or hydrogen. Again, too far away from myself. Okay, and if I bring in an ethyl Grignard, okay, so this is what ethyl Grignard is typically going to look like. The nice thing is if you are able to think about this chemically and say, okay, yeah, my carbon over here is actually my delta minus, my magnesium is actually my delta plus, then what you can do, which a lot of people find this a little helpful, is just draw it in more of an ionic form. That way you're not so worried about what the magnesium is doing, and you can put more focus on your carbon nucleophile, which is the important bit. So once you've got your carbon nucleophile identified, we're going to go and attack that carbonyl carbon. Okay, so because that's our delta plus. And we're moving our electrons to our oxygen, which is our delta minus. So then we get to this intermediate. Oops. Okay, so we've added our ethyl group in here. We still have R1, we still have R2. And the thing to keep in mind here is at this point, this is pretty stable, right? We kind of went from a position where we had more of a C minus to now an O minus. So we're definitely going downhill in energy because this is really reactive and this is less so. So once we're here, we kind of look at this and say like, yep, it looks pretty stable. It's definitely more stable than what we started with. And in fact, it's not going to be able to do anything else. And we're going to come in with our acid quench. We're going to go quench that. The other thing we're going to quench is any remaining bits of our Grignard. Okay, so any of that left over from our process will also go through that quench. So we protonated that O minus. So now we have an alcohol. And then we've also protonated our Grignard, where we originally had 2. And now we're going to have 3. Okay, and then our magnesium bromide is just going to be a salt left over in that water layer. Okay, so again, just because we don't really care about the counterion in most cases, we don't really need to worry too much about that. You also don't need to worry too much about the fact that when you got that O minus, you really do have an MGBR hanging around with it. So it's just going to be acting as a counter ion for anything that's negative. So just kind of keep that in mind. It is floating around. It does not stay. So most importantly, it does not stay over here because now this carbon is perfectly neutral and stable. So that's the reaction with aldehydes and ketones. And this is going to be the same mechanism with sodium borohydride, lithium aluminum hydride, and organolithium reagents. Okay, all of them are going to look exactly the same. So then if we go on to the ester and acid chloride world, okay, things are going to look a little bit different here. So we're going to have probably some sort of carbon or hydrogen in R1, and then we have an X. Okay, so our X is going to be an OR or a Cl. Those are the ones that we're going to work with the most. And again, our R1 is going to be a carbon or hydrogen. Okay, so we can start off with this the same type of way. So let's start with an organolithium reagent this time, just for fun, just to show that it really is all the same stuff. Same thing, we're going to go and attack that carbonyl carbon. Where now I've got my addition of my 2 carbon pieces. So at this point, now if we're thinking about this X as being an OR or a Cl, okay, I'm just going to kind of put that in here. Okay, so maybe we have an OCH3 to make it an ester, we've got a chlorine to make it an acid chloride, one of those 2 options, then this is not a stable landing point. Okay, one thing that we're going to see over and over again is that the lure of the carbonyl is strong. So we can push those electrons back down into a pi bond and kick off our leaving group. Okay, so this loss of leaving group step, we've kicked off our X minus, is going to leave us with this ketone. So very important here, X minus really depends on kind of how stable it is as that anion. So make sure when you're kind of kicking things off that you're thinking about it in terms of, if I were making this into a conjugate base, is this stable, right? So that's kind of a good rule of thumb in terms of leaving group ability. So chlorine, bromine, iodine, those are good leaving groups. Fluoride, not so much, right? OH minus, not so much. So we're going to be kind of diving into that idea a little bit more, but just kind of think about, like, is that going to be a reasonable anion? And things like carbon, things like hydrogen, kicking off C minuses, H minuses, that is not possible, okay? The only reason we have a C minus up here is because we've got like some other stuff going on in terms of the magnesium and all those things. So once we have our ketone, then we're basically up in this world, right? Where we have a ketone in place. It's still reactive. We still have our starting material around. And so then we can just get a second reaction occurring. Until we get to a situation where at this point, we have no leaving groups present. So we have to stop there, right? We can't do anything else because we're basically in the same situation that we were in on this side. So now we do our quench again. Okay, again, that's going to quench any remaining bits on our organolithium reagent. And that's going to get us to a tertiary alcohol here. Okay, so just kind of keep in mind, you're really looking for esters and acid chlorides are going to be that kind of point here. And the limitations on this is that we cannot be adding 2 different nucleophiles and expecting them to add like one at a time, very orderly. And it's also really, really hard to stop it from reacting with this ketone by only adding like one equivalent, okay? Because this ketone is more reactive than an ester. So you're going to get some weird mixtures of things. So we want to always assume excess of our strong nucleophile to get complete reactions every time. Okay, so up here, we probably have more than 2 equivalents of that organolithium. And same thing with a Grignard or sodium borohydride, any of those, we would have more than 2 equivalents for that reaction, so that we could add it 2 times, because like I said, you're going to get a horrible mixture of stuff if you try to do it with just 1 equivalent and trying to get to that ketone. It's just not going to work. There are ways to do it, but we're not going to talk about them in this class, but I'm happy to talk about them in office hours if you would like. Okay, so this one is going to be the same mechanism. With lithium aluminum hydride and Grignards. Okay, so any kind of Grignard reagents. Our note here that we want to keep in mind here, though, is that sodium borohydride can't react with esters. Oops. Okay, esters are not a very reactive electrophile, and sodium borohydride is one of the weaker, less reactive nucleophiles. So those 2 things are just not well paired up to do reaction together. But in other cases, these 2 mechanisms are going to take you through most of what you need for strong nucleophiles with carbonyls. If you have any questions, let me know, and I will see you all later.